Yeah. Big deal, but you know. Yeah, I would have this discussion.
All right, welcome everyone. This is H2O, Machine Learning, Big Data Science, and I'm Arno Candel. I'm from Switzerland, you might be able to tell from my accent. Most think I'm German, but I'm Swiss. But it all started here in California at Slack, and then I went to another machine learning company in 2012, and I've been at H2O for a little over a year now. Doing supercomputing applied to machine learning. So my background is all about high performance computing, physics, and math. And last year I was nominated and then named the Big Data All-Star, which was nice. Let's see what this year brings. So this year was another thing, was KD Nuggets. If you read this interview by any chance, this was a 3-part interview with KD Nuggets about H2O and deep learning and all that. So if you're interested in that, and the background in physics, how that all relates, that's something that you can look up. Just search for my name for KD Nuggets to find it. So today we're going to talk about deep learning, but not just deep learning, also a little bit about H2O, about the future of H2O, about how it works, what it does, how it's being used by people, and I want you all to be able to walk away tonight and actually run H2O on your Hadoop clusters or your laptops, on data sets that are tens of gigabytes, hundreds of gigabytes, or even just 10 megabytes. It doesn't matter, right? The idea is that this is a scalable solution for machine learning using the latest and greatest techniques in supercomputing, in math, in software design, and you'll be able to see some of this tonight live. So I'm going to run some live demos as well. So the hands-on session, that's as much as we can do later after the talk is over. You guys are welcome to ask me questions and I'll show you what we can do here live. But mostly we'll do the first part tonight. Of course, this is a teamwork. Shri and Cliff, our founders here. Cliff basically wrote large parts of the Java compiler, the hotspot compiler that you can download now at Oracle's website, formerly known as the Sun Java compiler. So he knows exactly what he's doing in Java land. We have, I think, almost over 30 people right now in this company, big office, everything's great. So this is a nice teamwork, and we have Stephen Boyd, Robin Shirani, and Trevor Hasty here pretty much every few weeks. Stephen Boyd was just here for a whole afternoon the other day, I think a few days ago, and we discussed the latest, greatest new machine learning techniques, and we're going to incorporate those into H2O. Of course, they have written these books. If you don't know, they are the gurus of machine learning. And this is also an open source GitHub repository. Everything is open source here, and it has about 60,000 commits by now, and that's in 2 years. Apache Cassandra has 16,000 bits over 5 years. Just to give you an idea, this is a high velocity project with a lot of contributions in a short amount of time. It's also the #1 machine learning repository in GitHub for Java, which is also the #1 language. So HTML is basically on top of some data. So you need to provide the data. You can massage the data with Spark, for example. In our new HTML sparkling water project, you can do stuff with RDDs in Spark, and then whatever comes out of this initial pre-processing, we can then pipe that into HTML in the same JVM, and it's effectively taking the data from wherever, whether it's HDFS or S3 or a flat file in NFS. It just takes the data in, distributes it on the cluster, and then does some work. We have connectors to different clients because this work is being done by a distributed system of JVMs, Java virtual machines. Every node runs a JVM. And every node itself responds to a REST request, like a web server. You can say, hey, run this model, or show me what you have, and so on. So you can actually talk to each node. And these clients like R or Python or the web interface, they're literally talking to this node that you're talking to. You can say which machine and which port, and that guy will then respond with a web page or with some R, basically some stuff that can be displayed by our R package that we have to make your life easier from R, or the same holds from Python now. So you can literally connect to any of those 60 nodes if you want. It's your choice which one you want to connect to. So that's the basic idea. It's a distributed peer-to-peer system of JVMs that are basically just memory storage systems. Right? Each one is defined by how much memory you can address. And of course, how many cores you have to process the data. And since we have Cliff here, modern experts in Java, we don't have garbage collection issues. If you think that Java is slow, think again, because you don't have to do stuff that's slow in Java. You can also write it in kind of a Fortran or C style. For the things that matter, that's what we do. We have a long array of bytes that stores 1 million numbers or so, and that's our data. It's our own compression. If you have data that's all ones and zeros, you don't need to store them as integers or longs or doubles, right? You just store them as bits, and so on. If you have numbers from 1 to 10, you need only a few bits to represent that, and we do that as well. So you don't need to store doubles. That's the basic idea. You only need to store what you need to store. It's a lossless compression. There's about 15 different schemes to compress numbers. For every, let's say, 10,000 numbers or so, there's a different scheme that's been picked. And each vector, each column in your data set has its own scheme per maybe a few thousand numbers. So there's a lot of little schemes everywhere that are being applied to compress the data. And also these chunks, as we call them, they're being processed by our map-reduce paradigm. So you process the data in a map, and then when you're done computing, for example, a sum, you reduce it back, and the reduction is done by different threads. We have multiple threads processing the data. They reduce immediately in memory as they're being bound up. Basically, as they finish their job of processing the data, they immediately collect the data and collect it together in this reduced state. It doesn't go back to disk like Hadoop's packages. So it's much more efficient than Hadoop. It can be 1,000 times faster than a Hadoop-based, disk-based solution. Of course, it runs on Yard and Mesos and MapReduce v1. It has an R package from CRAN. You can just import the package itself, a one-line command. And we have also a scoring engine. Basically, they export Java code. You can just take and put it into production somewhere else. You don't have to run HTML to make a prediction. Once you have a model that's trained, you just export plain Java code. But I'll show you that later. So we have a bunch of algorithms pre-made so that you just use them. So tonight we're going to focus on deep learning. Basically, that was done in the last year and a half or so. When I joined, it was still early, but then we matured the product. And now it's one of the workhorses because it just works. And I want you to try it and tell me if it doesn't just work. It's normally deep learning is complicated. People have a lot of respect of deep learning, but I want you all to be able to try it and say, oh yeah, it works. If it doesn't work, it's not work. So the idea of deep learning is that it somehow figures out nonlinear transformations, multiple nonlinear transformations that are stacked. So you first take, for example, some pixel values on face, and then you convert that into some weird features, like some different dimensional space of numbers that are somehow non-linearly mapped from the original pixels. And then you do that again and again and again. Each time it's a non-linear transformation. And that power of the non-linearity that's aggregated, that's what really defines deep learning. So it's not the same as, let's say, a linear model by definition. It has to be non-linear. It has to be multiple such transformations. So an old school neural net, let's say the RNet package, that's only one hidden layer that would not qualify. I'll show you later what that means, a hidden layer. SVMs, kernel methods, trees, they're all not. They make up non-linearities, but they just say if age is less than this and income is less than that, then you're in that corner of space. But it doesn't take something like age square minus income and then square root of that. It's very hard to make that up in trees. You can do it, you can approximate it, but it will take you way more trees than in a deep learning system. So if you have non-linearities in your data that you don't have in terms of features, you want to use deep learning. So what we define as deep learning is a standard feed-forward neural net. And most of the time it's supervised, but we can also do unsupervised learning, where you just learn the structure of the data. And I'll show you a demo later. But for now, the idea is that you learn something by repeatedly showing the data, the training data to the network. And it gets smarter as time evolves. The more it sees, the more it gets used to the data. And it learns an efficient compression technique. It's basically trying to compress the data into some system of numbers that somehow represents the data as well as it can. For us, distributed means many machines. Multi-threaded, of course, means all the cores are busy. So this here is a display that says if it's green, it's busy. And I'll show you that later. You see that here, in this case, there's actually 20 cores on our 10-node system back there that's totally busy doing deep learning. So this can be a lot faster than an old-school neural net implementation that's single-threaded on one machine. And of course, we have all the latest and greatest techniques in our deep learning implementation. I might not be able to read this, but automatic standardization, categorical values, missing values, initialization of weights, regularization, adaptive learning rates, momentum trading if you want, dropout, L1, L2. We have grid search, info cross-validation. What else we have? Load balancing, auto-tuning of the amount of communication versus computation. All these things are automatic. Model averaging. So you shouldn't have to do much other than to say go. And maybe specify the architecture of the neural net, like how many layers you want and how big those layers should be. Maybe one or two numbers for regularization. That's about all that you do. So this is a neural net. Imagine you have three numbers, age, income, and employment. You might wonder what number should I put for employment, so think about this for a second. These numbers somehow propagate into the next layer, which is hidden neurons, which are just also basically each of them represents a state. I'll show you that in the next slide what happens, but you have to imagine that the information flows forward. At the end, you have two numbers here, one for married and one for single, and that's your probability of being either one of those classes. That's a classification, binomial classification. And the number of connections is what defines the number of weights. And then there's a couple extra numbers that is bias terms, but that's basically all small stuff. So what really matters is the product of the number of neurons in the input layer and then each hidden layer that just each one of them is a matrix, basically. So this is a matrix of 4 by 3. And in reality, you might have 1,000 by 1,000, so you know there's a million numbers that it has to learn. And that for each layer, of course. So what really happens is you add up these numbers in a specific way. You sum over xi times ui, where xi are the values, uij actually is a connection between the I neuron and the j neuron, the next layer. So you just sum up like your contribution to me, your contribution to me, your contribution to me, your contribution to me, and so on. You add it all up. And then I apply the pan-h function, for example, or another rectifier, some nonlinear function that somehow is somewhat linear in some regime, but maybe flattens or flat lines in some area. There's different methods for finding these functions, but it turned out that the rectifier is very powerful because it's easy to compute. It's just either 0 or x itself. It's a super simple function, and it doesn't saturate, which means it's able to create bigger signals, which might make it less stable, but with modern techniques, such as adaptive learning rate, you can actually train these efficiently. You don't blow up. Otherwise, you would worry that if you have too many big numbers, they all multiply or add up together, then somehow this whole system becomes exponentially unstable. But we can actually train this nowadays. All right, so back to what happens. So this number here is not computed as a sum of all the incoming numbers, and then you apply some non-linearity. That makes the whole thing non-linear. And then to get to multiple levels, to call it deep, you have to do this again. So each of these numbers was computed from the previous layer, do it again to the next layer, and so on, until you're here. And now you have 3 final numbers that go into these probabilities, and we do that with this softmax function, which is basically just saying, first apply one more sum, but instead of doing a tan-h nonlinearity, you just like sum up these contributions into this guy here. And let's say this is 12 and this is 7. We need to map them into the space of 0 to 1 because it's probabilities, right? So the 12 and the 7 get somehow normalized with this formula. It's just exponential function of 12 divided by the sum of exponential function of 12 plus exponential function of 7. It just normalizes it back into the 0-1 space. And then you have your probability. Now, of course, the question is, how do you find these weights? Here, these u, I, j's, and y, v, j, k's, and so on. You also notice maybe that there's a v, j. This is like a bias term to add to each of these neurons. It's basically an offset. It's like your real brain, right? The nerve neurons might not fire immediately. They might only fire once you have 30 millivolts or something of potential difference. But anyway, this is basically just another degree of freedom to give those neurons, which can be trained just the same way. So initially you have to find some numbers for these weights. You can't just set them all 0. If you set them all 0, the whole system will not learn. You have to initialize it with noise. So what you normally do is you say, just initialize it with some random weights. But pure random is not great, right? If I say minus 5 billion and 16, whatever, that's not good. It has to be somewhat small. So you want to normalize it with maybe a Gaussian distribution, standard distribution, or a uniform distribution. And we have this method here that computes it accordingly to this formula here, based on how many neurons you have in the previous layer and the current layer. So let's say here, this has 4, this has 3. These weights all have to be a certain amplitude to not make the system blow up too much. Let's say this was 1,000 neurons, and my weight would be the same size as for this case before, then it would add up 250 times more numbers, so that might be too much. So we have to divide a little bit more. And the formula is here. It says how to divide it so that it doesn't blow up too much. It's only the square root, similar to a random walk idea, for those who know what I'm talking about. Otherwise, it doesn't matter. It's basically just some smart initialization. That seems to work fairly well, but there's also options to manually say, no, I want this amplitude to be 3 plus minus 3. That's the space in which I want to standardize it in. that's how much sigma is of my Gaussian distribution. So we have all these options. Now think again about employment. I said earlier, what's the number for employment, right? You don't want to just say it's 0.3 or 0.4. There's no such notion of an order in employment maybe. So in reality, it's a categorical variable, and of course that means it's either this or this or this. In this case, we have my example, it's either full-time or part-time or non-employed or self-employed. So these are 4 different options, and to encode those, we do this the following way. We just have 3, one less than the number of options, 3 binary indicators that say, am I one of those 3 things? Am I full-time, yes or no? Am I part-time, yes or no? And so on. And if you're neither of those 3, then you're the last one. That's why we need 1 less. So basically, we turn employment into 3 numbers. But if you have zip codes, that would mean you have 70,000 numbers. The neural net suddenly becomes a lot bigger. The initial input layer is 70,000 long, right? Which will be very slow. So what you really want to do is you want to embed those 70,000 zip codes into maybe a 10-dimensional space. And there are methods for that. So you can use some kind of PCA or so to reduce the whole dimensionality of some of these categorical factor levels. And that will help a lot. Because deep learning is good with numbers, but it's not the best for 0 and 1s that are just totally sparse. Because it will make it dense. Because all these weights are some numbers over there, and it'll learn if single 0, 1 doesn't matter or not. That's going to take a while to train. So keep that in mind. You don't want to have too many factor levels in your input. So let's say you have something that says it's 0.8, my prediction there at the end of the softmax, and the other one is 0.2, but in fact it should have been 1 and 0 because we actually were married. There's an error, right? The mean square error is 1 error, and you would just compute the error for the class and then square them up, add them up, divide by 2, and that's your mean square error. Now you could say if you have 10 classes, what does it mean if I have 10 numbers squared and added? All I really care about is the 1 class that I should have been. Right? Class that says I'm a human, let's say. That's yes or no. I don't want to know whether I'm a cat or dog or mouse. I just want to know whether human is good or not. So for that, there's this cross entropy, which basically says if you're not 1, the error goes up as much as the logarithm goes down. If you go less than 1. This is a pretty strong penalty for being wrong. That's what we use for classification. That seems to be very useful. But if you like, you can also switch back to mean square error, which makes it more even. But this one is good if you really want the 1 class to be right, that you should have been. So now you have an error. You know how wrong you are. And this is your error function as a function of the weights. Each weight is like a very high-dimensional space, right? In our case, we had maybe 20 or 30 weights total. But if you have 1,000 neurons and so on, you get 1 million of these weights. So you have a 1-million-dimensional space in which you have some energy landscape or an error landscape. That's the physicist to be talking. So you want to minimize the error, and you need to find the lowest point in that landscape that's 1 million dimensional. That's not an easy problem. It's not a convex optimization. You can't just put some penalty on and say find the lowest point. But that's what we do anyway. With some stochastic gradient descent, it actually works reasonably well, especially with some extra tricks we're applying. But the idea here is to find the gradient of your space, see how steep it is, and then follow that gradient down. And then you follow it down by as much as the learning rate says. If the learning rate is high, you go follow that arrow more. If the learning rate is low, you stay basically put at the old place. And now each of these neurons has its own learning rate. So you have 1 million of these learning rates for 1 million neurons, and each one remembers how much it should be changed basically the next time it gets updated. So it's a very powerful method, it's adaptive learning rate. It's much better than a global number for the learning rate. And once you figure out this number automatically, then you all you need is basically the gradient to know how steep is it. And to compute the gradient, we don't do the naive approach where we just change the weight, each one of the 1 million weights by a little bit up and a little bit down and compute the slope. That would be too slow because that would be 2 million evaluations, right, for the total loss function. So what we're actually doing is we're back propagating here. It's using the chain rule. There's a way to compute all that prove that this is the right thing, but the chain rule basically says you only need to know the derivatives of each thing here that maps forward. There's a derivative that you have, you can just back propagate all the numbers in a kind of a matrix multiplication way. Just push it through backwards and apply those deltas, those fixes, those changes to the weights automatically. So that's a very powerful thing. Came out in like the late 70s, I believe. So it's not new, but back then it was too expensive to do any of this. Only now machines are fast enough to actually do deep learning. And also there's a couple extra tricks like dropout, like adaptive learning rate, that make this all work. But in a way it's also old school stuff. A lot of this was invented in the 70s, even earlier. So what we do in H2O is we have a model, initial model here, my weights, I call that the model. And we put it into the KV store, our distributed key value store. Our distributed JVMs, they all have a little bit of an object in Java that says, that's my store. And you put something in, and then it notifies everybody that there's this key. And everybody, all these 10 machines can then say, what is this key? And the one guy that owns it will send it to them. And it's always a consistent view of that key. So it's like a Java memory model, but made available on a distributed system, which is very powerful. So what we do here is we take the initial model, randomly initialized, we put it in this KV store, and then you can immediately go to the browser and look at it and say, what is it? And I'll show you a demo of that just after this. And this model now is available. And what happens is it will be spread across the machines in a logarithmic way. Like one guy sends it to 2, and they send it each to their next 2, and so on, and it spreads exponentially. And you have only a few steps of communication. That's supercomputing principles, basically, that you apply here to get to all the machines. Then they all have a model. And then they train it with all the threads. And all the threads are racily competing for reads and writes on those weights. There's only one set of weights per node. Each compute node has one weight matrix. As many as there's hidden layer connections, right? But there's only one model. And that gets updated by all the threads. So you have 32 threads. They all say, read this number, multiply forward to get prediction, and then see what's wrong with it, and apply the correction point by point. Each single point gets a streaming way to modify the weights. And each thread is doing that in the map phase of the map reduce. So this is the map phase here. From here to here, this is basically the map phase, but it's the spreading that belongs to the map phase 2. Now we have 4 different models, 1, 3, 2, and 4. And these different models are slightly different because they're trained on different data, right? And they have different race conditions between the threads, so they cannot be all the same. So what we do is we average them. There's a paper that says that this is a good idea, but there's no real proof for that. It's all race conditions and you average, so it's not much you can prove mathematically, but in a way this turns out to be a good average. It's not an ensemble model, but it's kind of related. It's not the average of the predictions, it's just the average of the model itself. So we have an average model here, and that guy gets pushed into the KV store and may be scored. You can then predict how good it is, see how many samples have been trained to that point, you can do statistics with it and so on. But basically, normally what happens is, once you made this copy here to new ones, you immediately start the process again, pass another map and reduce over the data. The more of these you do, the better it gets. Each pass here can be over as many points in the data set as you want. It can be 5 rows, or it can be a billion rows, more than your data set. You just keep repeating. Or it can just take a subset of sampling. So it's in a way it's similar to a random forest or so, where you do a subset, a bag basically of points that you process. And one pass over the full data is called epoch. So if you have 1 million points in your data set, once you have 1 million training samples, you've seen 1 million, we call this an epoch. So these are again the secrets to a good deep learning model, as far as I know. So you have adaptive learning rate. That's very important. You don't have to worry about these fine-tuning things there's like 7 knobs, right? You have the initial learning rate, you have the decay rate of the learning rate itself, you want to increase it, you don't want to be learning too wildly. So there's an initial rate, there's a decrease, there's a final rate. Maybe you have that, or the day time. There's a momentum term initially, then the final momentum, and also like how long it should like decay or whatever for the momentum itself. And then there's whether you have this type of momentum or different type. It's called Nestanov accelerated gradient. All these things, the 7 parameters for a learning rate. And this is just one number or it actually takes 2 numbers, this one here, but you can leave the default. I never seen a model that didn't converge with those default numbers. So basically you have no worries about learning rates anymore. The regularization, L1 says find weights that actually matter. Everything else gets driven to 0 because it's basically a hill that you're climbing like this, right? It's the linear potential. It pulls you down really fast. As soon as you're not at 0, you're gonna get pulled to 0. If you want to stay away from 0, you better be a really important weight. You constantly have to climb uphill. And that's only happening to good weights, those that matter. This basically forces the system to become sparse. Like, let only important stuff survive. L2 is this kind of potential, right? Quadratic, where stuff that's around 0 is not too expensive, so you sort of allow those guys to float around, but you don't let anything go too big. It's basically best of everything. Dropout is when you say, some of my input, for example, I don't want to see all the time. I just see 80% of my input features. I don't need to see every single zip code all the time, or every single pixel of my image. Because if I do, I overtrain and learn and memorize just the exact pixels of my training data. And once I come with a different test set, suddenly it's different, and then I don't know what to do with it. So you can regularize much better if you have dropout, but only if you have a lot of features. If you only have 12 features like age and income, you don't want to blind away from those, right? You don't want to just ignore age, for example. So it's not always a good idea, but it can be a good idea for noisy data with lots of input, lots of predictors. This dropout also applies for hidden layers. So let's say you learn something in the first layer. Those learned neuron state activations, you can also ignore a certain percentage of those, a random percentage. Per point, it's a different random percentage that you ignore. That's basically saying, I don't care about every of those learned higher nonlinear features. I only care about a subset of those nonlinear features, but a different subset each time. So what you're doing really is you average billions and billions of different models. Each one has a different architecture. So this is like a super ensemble that's happening in real time, right? It's very powerful. Then of course this race condition that we mentioned earlier between the threads, it's called odd-wild, that also generalizes in a way because it avoids learning too well. Because the different threads, they read and then someone else overrides it, then I write again, apply my delta, and it's all wrong, but it's okay, it's not too wrong, it's just slightly off, right? And that gives you some kind of generalization as well. And the multi-model averaging also is generalization. So all these things together in a distributed system actually work together to make the model better in terms of test set accuracy. Then there's grid search, and there's cross-validation and checkpointing, all these things. I think it's almost time for a demo. These are details, like you can look it up later. This is what the learning rate is doing with this adaptive thing. Basically says if it always was updating a lot this weight, then keep updating a lot. And if it suddenly has a big change in the behavior, then adapt to it. Don't just freeze it in place. Suddenly there's a requirement to change because the gradient is big, then you're allowed to change it more. And dropout is pretty simple, right? Just ignore a certain subset. There's a reference to Jeff Hinton's paper, who's now at Google. All right, let's do a demo here. Who knows the Higgs boson data set? Anybody seen this before? Okay, great, not too many. So this is particle physics, right? Who knows the CERN LHC experiment where they found the Higgs boson, the God particle? Okay, so this is where mass comes from. Biggest experiment of humankind, $30 billion, like a big thing, 16 miles, big tunnel on the ground, superconducting, temperatures at basically 0 Kelvin, which is very cold. And this thing is a detector that makes some measurements, and it has some numbers for it, like voltages or energy, call it calorimeter or something like how fast is particle flew into this thing. And these numbers that can come out are 21 numbers. For every event, there's 21 numbers. And that's just one experiment. In reality, there's like way more than that. But let's say this is 21 numbers, and from those you have to judge whether this is a Higgs particle or not. Simple problem. Now the physicists, they came up with some formulas to make up better features in addition to the 21. They made 7 more based on their knowledge. If you know forward momentum and total energy, you can compute transverse momentum or something like that. And it's just like 1 minus the other and then square root of it or something. And they compute that. And then when they add it into the mix of the 21, you have 28 suddenly, and that's a much better model that you can build with those. So there's a paper in Nature that said if you only use the low-level 21 features, you get like a 73 AUC. You know what AUC is? Who does not know what an AUC is? So that's basically a number that says how well you can predict. AUC should be 1, then you're perfect. If it's 0.5, it's basically random. So you want to be above 0.5. And 0.7 is kind of okay, but it's not great. Basically, almost a coin toss. Not quite, but it's still halfway there. So once you add these high-level features, you get to 81 AUC. If you do only the high-level features, you're at 78. So the high-level features seem to help. Now this paper said that they're using deep learning there, right, for this. So let's see what we can do with that. So I tried to do the same thing with H2O, with the low-level features alone. Using a generalized linear model, they got to a 0.59, so it's really not that great. Random forest, 75, 76, gradient boosted trees, neural net also, so all these methods that are kind of simple methods in terms of non-linearities that I can express, they get to a 76. And that's with fairly heavy tuning. So I tried my best to beat the CERN people that had a 73. And we were able to do this, actually not too much tuning, but maybe an hour time or so for each method. And that's a Nature paper that I spent a year on. So we have a better baseline algorithm than CERN scientists, which is good news. But now also we of course want to run this in initial deep learning to see how well you can predict using deep learning to make up those formulas from scratch without the physicist writing them down. And you see what you can expect if you add the right features, then you get to 83, 84. So we also beat certain people. So let's do a demo. I have a cluster up here. How do you know it's a cluster? It looks like a web page. You can go to cluster status. You can see it number 10 here. I'll make it a bit bigger. You see number 10 here. There's 10 machines. IP address port. I can click on this guy, and then I'm going to talk to this guy, 184. And it also sends me a status of what's happening here. It shows me its store, what's in its store. But they all have the same store, the global view of the store, the things that are in the store. So right now there's a Higgs data set. The data set is 11 million rows. It's 29 columns. That's including those physics features that are added. And it's basically available to view here. But of course you don't want to go through 11 million rows, so that's just an easy way to see that the stuff is same. What you can do now is click on generalized linear modeling, for example. You can say my response is the first column. Call this GLM 2. I already made one earlier. I'll just show you how easy it is. I ignore the last 7. Those are the high-level features. 7. It's a binomial problem. Yes or no, right? Higgs or not. And everything else you can leave at default option. Go. So now it's running a generalized linear model on those 11 million rows, and it's already done. So I just computed it, and it got a 0.594, as I said earlier. And this is the AUC curve. If this was a diagonal, it would be worthless. If it's an energy function that goes like this, it will be perfect. It's kind of far from perfect because it doesn't take the non-linearities into account. But it's very fast. Okay? So,
Can I ask you a quick question?
yes?
So how does it do on kind of out of sample type of data or whatnot? Or is this all in sample that's been trained on, or is this out of sample type of data?
GLM, yes, this is for GLM on in sample. This is its own training error. However, GLM is hard to overfit, right? If you have only like 20 or so numbers, like for each coefficient you have a number. For each predictor, I mean, you have a number that says how important is that. So for 20 numbers, you cannot possibly overfit a 11 million times 30 data set. So this is 11 million times too little, too few numbers to actually overfit. If you have a deep learning model that has, let's say, 20 million weights, or a random forest that goes very deep and has a lot of trees, then you're able to overfit and actually memorize the whole data. In this case, there's no way to memorize it. But you're writing this training. That's why I actually split the data into 3 pieces. Go back to the store. There's data, and you can do a lot of things like import files, compute certain things, impute missing values, split the frame or create a random frame and so on. But I did split it up into 3 ways here. Part 0, part 1, part 2. Part 0 is 10 million rows. That's my training data. Part 1 is 500,000, part 2 is also 500,000. So one of those we use for pure training. This is then the in-training validation to see how well we're doing for, let's say, a grid search or something. And then this is the final testing where you can say, let's see how good we are. So let's now build a deep learning model on part 0 here. So I say deep learning. The response again is the first column. I ignore everything that's human-made. I specify the second piece as a validation set just to get an error that is meaningful, because there is a slight chance that we overfit here, but still it's not really a chance because the models that I'm going to build right now are not that big. I turn on the expert mode just to show you that, and then I'll say, let's see, what do we want to do? We want to do a grid search. Let me do a grid search over something like a 3-layer and maybe a 4-layer net. Okay? Something that's really fast and something that takes a little longer. Of course, this one is most likely going to be more accurate, but we only train for 10 passes over the data. Just a quick idea of what's happening. This adaptive rate says you need only these 2 numbers here, rho and epsilon, which you can leave default. It's fine. You don't need any of these here because this is all just for manual learning rates. You don't need any input dropout because you only have 21 features. You don't want to miss any of those detector features, right? They're all important. L1, L2, doesn't matter too much for a small model, but let's do something here. Let's do L1, L2, delta minus 5 is a small number, it's fine. Just do a little bit of damping if you want, regularization. This says how much you want to constrain the squared sum of incoming weights. Like if I have 1 neuron and I have all my incoming neurons, if this adds up to too much, then I'm in danger of being exponentially blowing up later, right? Because if I have too many values contributing to me, and I have a rectifier function, which is what that shows up there, rectifier says just add them all up, and that's what you are. No nonlinearity here. The nonlinearity is if you're negative, then you're 0. That's the nonlinearity. But if you're positive, that's what you are. So in this case, you could add up too much. You could blow up exponentially. It doesn't happen very often, but sometimes it happens. So if you have like a 6-layer neural net or a 10-layer neural net, you want to turn this number up to maybe a 10 or something, which says once it's more than 10, this incoming sum of numbers squared, then scale it back to just 10. Keep it small. Just reduce the weights globally, like everywhere. Just make them less intense. You still get the same distribution of the weights, but just tone it down a little to keep it stable. Initial weight distribution is adaptive. That's the default option. That's this one with the square root of 6 here. The loss function is automatic. In this case, it would be cross entropy. So these are just options for scoring, how often you want to score. 10% of time you can allocate for scoring. Score only 10,000 points for the training data. That's good enough to get an idea how good we are. We don't need to tend to spend too much time scoring millions of points. We stop once we hit 0% error on the training set. That's as good as we can do. But sometimes you want to set this to -1 and continue training forever if you want to do better regularization, for example. There's some other options. You can balance classes in case you have a 1 in 1,000 event, so like a frog. You can show variable importances. Let me turn that on. And the rest you can leave at default. So now I say go. This will actually make a grid search over 2 models because I specified 2 different architectures here, right? One is the 3-layer, one is the 4-layer layer. And now it's creating at the end here. See this, this key here. If I click on it, you'll see the model. This is now asking the KV store, the key value store, on that machine. Hey, go fetch the model from whoever owns it and display it. And here you see a 3-layer neural net, 21 input, 2 output, rectifier units, no dropout, some L1, some L2. This is the statistics of how much are the learning rates right now. Each layer is slightly different, as you can see, and the weights and the bias terms, just to see that stuff is same. And now here you see the real-time evolution of this. If I do a reload, it's going to be better already, most likely. Yep, it's already 76. This is already as good as a random forest ever would get. Or a GBM. We just did this in the last few seconds, right? So this is the deep learning model that's now learning these nonlinearities of the Higgs problem. And this is on the holdout set. This is on part 1. But training is on part 0. So this is the actual validation error. And you can see a confusion matrix here as I move my mouse over this AUC and the ROC chart. The AUC is the area under this curve. That's actually the number, 0.76. If I move this around, I am looking at different true positives and false positives. You have to balance those two, right? So if I say my threshold is 0.6, or let's say 0.4, if I say once my probability is 0.4 of being a Higgs, I'm a Higgs. It doesn't have to be 0.5. I just say 0.4 is good enough. Then I'm here. I have a lot of false positives, but I have even more true positives. So you're kind of balancing those two. If you really wonder, like, what's the best point, you can say this is the best. That both class errors are as low as possible. And you see 0.54 is where it should be. So there's these kinds of things you can do. And there's also variable importances here. In this case, you have feature number 7 is the most important one.
How do you know it's a true positive? What do you compare it against?
That means my prediction on the validation set said it was a Higgs, and it actually was a Higgs, because I have the points labels, right? In my training data, the original one was 11 million, and it had a label for each one of those saying yes or no, I'm a Higgs or not. So I have the answer for every single point. But I'm not using this. I'm just using 10 million to train, and the remaining million I hold out for validation. I make a prediction on that, 500,000 of those 1 million, and I say it is a Higgs. And then I look, and is it really a Higgs or not? If it really is a Higgs, then it was a true positive.
I thought the whole purpose of this experiment was to determine if Higgs bosons even exist.
That's not this one.
Yeah?
This is not it. This experiment is, this is basically used problem, right? It's not the ultimate problem. It does Higgs exist? This is more like knowing what a Higgs should be like from Monte Carlo simulations. Can I find it? And then they actually apply this in the real world later. But this is like the supervised training part of things where you know the actual answers. Just like you know which people left your company or churn or fraud or whatever. You need some labels.
So how many Higgs bosons are there? How many ones were there in that?
It was about half-half.
It was 50 years, okay.
That was, of course, a prepared data set for simplification. The Nature paper provided this data set. In reality, it's not 1:1, right? It's more like 1 video or something. So in reality, it's much harder. But they made a model that just is good at detecting it. They worry about this readouts and stuff. So you see how fast it learns. After 20 seconds, already has a 75. If I reload this again, of course it's long done. I said 10 training epochs, and it's done after 2 minutes. Now it's at 78. So it beat all the other methods already. And this was this model with 3 layers of 100, super fast. It trains almost 1 million samples per second. And it's fairly efficient at learning these non-linear areas. But you remember I ran a grid search when I go to jobs. I can see that there's a grid search. The second one is almost done as well. Let's go look at that one. With the 4 layer of 200, that's now at 78. So it's not quite as good yet, but it might get better if I train this longer. Right? If I let this run for another 10 minutes, it might be much better. Let's let this finish. Actually, we can, for fun, we can, now that it's done, we can run it a little longer. So it's done. Yeah?
Could you talk about how the variable importance is calculated?
Yes. It's based on the weights and the magnitudes and the signs of those weights. So there's a paper by Gedeon, I have a citation somewhere, which basically says, starting from the input, how much am I being used to go to the next hidden layer? And then from there, how much am I being used again? The weights that go into the first hidden layer and out of the first layer. That tells you kind of how important the input is, right? So you follow the weights, but it's not trivial to do this. Like in general, it's very hard to put feature importances. Let's say you have 2 features that are similar, almost the same. If you leave this out, it's still the same result because this one is here to replace this one, right? So it says not important. Then you take this out, and this one does the work. It's also not important. Then you take both out, and the model is garbage. So they were both important, but not alone, right? They're only important together. So these correlations, they mess with you with this whole thing. So that's why it's a good idea to first decorrelate those features somehow and make it like better data that's more orthogonal. Then you compute feature importances. But of course, then you don't know what each feature means because you already processed them in a way. So it's very difficult to actually make meaning of this stuff. But this is as good as it gets basically for deep learning. It's not interpretable in general, but at least you know kind of what mattered. But there's papers that show the benefits, pros and cons of each method. This was the best method, but they all have their issues. So the best bet for you is to run a GLM and GVM, run a course like this, and then look at the summary opinion of all these models and what features matter. So this model trained for 10 epochs and got this done in 3 minutes, 78 validation AOC, and also 78 training AOC. As you can see, there's not much overfitting going on yet because we only trained 100 million samples, and we only have a few 100,000 weights or something. Let's see, 125,000 model parameters to memorize 10 million times 30 times 20. So that's 200 million numbers to memorize with 100,000. It's not going to happen, right? You're not going to overthink. So now I can continue training this model here because it's a checkpoint. You just keep training more, right? You just make those weights better. And I'll say everything the same. Just make another like, let's say 40 epochs. So now he keeps training. And then later we can see how well it did. So let's get back to the talk. So who has heard of the MNIST data set? MNIST is digits, or handwritten digits. So this is something that you have to do well if you want to do machine learning, or if you want to do deep learning in particular, because Jan de Kant, who came up with this first solution for this problem, said, don't get fooled by people who claim to have a solution to artificial general intelligence. Ask them what their error rate is on MNIST. And the world record right now on predicting 10,000 numbers from the 60,000 training set, which is all just digitized handwritten digits, is 0.83%. That's the Microsoft deep convex net. So 1 in 1,000, 1 in 100 is wrong, basically. And that's without distortions or enriching the data set with other stuff, or without using convolutions even. This is just looking at the numbers as numbers and not doing any image-like transformations on it. No ensemble either. So we get 0.83 as well, which matches the world record. So that's good news. And how did we do this? Well, we installed the package in R. We loaded the module. We initialized our connection to the server, to the 10-node server, saying it's running on this node. This is just one of the 10 nodes that you have to specify. And that's the port that load the training and test sets into H2O's memory, and then run deep learning. This was done from R, but R itself was not doing anything. There's no computation going on now. R is just sending us strings to the REST server, saying, please run deep learning. So it ran deep learning, 784 pixels, right, 28 square. The response is the last one. That's training data, validation data. Run rectifier with dropout. 3 hidden layers. Run 8,000 passes over the data. Do a little bit of L1 penalty. Drop 20% of the input randomly. Process all the points per math phase, like math and reduce. Every time you process, all the 10 nodes go over all the data, over all the 60,000 points. And then they average. That's what this option means here. And then never stop. Always keep going until you hit the 8,000 points. And then after 10 hours or 10 nodes, it takes a while. Like, this is really good after like a few minutes already, but if you want to get to this number, you need to run it longer. It gave this confusion matrix. And you see there's a 6. This means 7 and 2 got confused. Kind of a lot. So if I wanted to improve this model, I would take all the 7s and rotate them a little, distort them a little, and get better at the 7s. But just present more 7s to the system, maybe would also help. But you're not doing any of that. You don't do distortions, no convolutions, no unsupervised training, no ensembles, just regular, as if this was a churn data set or some other marketing or insurance or bank or whatever data set. Right? This is just numbers to us.
Quick question.
Yes?
Do people know what a human would do on the test?
I think it's 0.2%. So what you need is, you need convolutions, and then you get down to 0.2 or 0.3. Ensembles plus convolutions get down to 0.2. And distortions, I think. So you do a lot of reprocessing, you do Fourier transforms of everything, you do ensembles, and you do like 15-layer deep systems of deep learning nets, and then you can overfit this guy basically, because people know this test set as well, right? If I do this a billion times, and I see which one is the best for this particular test set, and then I publish it, of course I have to cheat a little bit, because I know the answer. But if I can get a lower number for the test set, I'm going to do it. Nobody said you have to train only on training them, and then at the very end, like a Kaggle competition, you get scored. You can keep training on this until you find something that works with the test set, basically. And of course, you only train on training. That's what you do. You only train on training. There's this learn.h2ai, by the way, is a good site for scripts and stuff that explain how to do all this.
Excuse me.
Yes.
By any chance, do you know how this error rate compares to that of the algorithms the postal service uses specifically?
No.
I've heard that.
I would guess they have 0.2, 0.3 now as well. I mean, this is all standard. This has been done in the last 5 years. Well, I'm not sure maybe they're 0.5 or something. They have more than just digits, right? They have all kinds of stuff. So I don't know what they're.
Well, I think they're especially good just on the subject.
So this is a model. It's still training, by the way. We're now at, let's see where we are now. We're at 0.81 already. It's pretty good, right? You can click. Let me go back to the model already built. For example, there's a tree method. know what a tree is, that's more intuitive. You can click on Java model, and then it'll say, oh sorry, it's too big. But there's a way to get to it by just changing HTML here, Java. And now we have a Java model of this gradient boosted tree method. And this actually is a tree here. Make it a little bigger. So it says, if this number is this less than 1.9, then this, otherwise this, and so on. So this is a long decision tree that's inline in the process. So this is not H2O anymore, this is just H2O generated Java code that you can take in a standalone application in like a Storm, Bolt, whatever, streaming real-time engine, or on your cell phone or whatever, and just make predictions. So this is nanoseconds because it's only the register of the CPU. So the CPU doesn't have to go to main memory to get numbers or anything. It's already in the code. The code itself is the model. Once the code runs, that's all it is. So this is and all the models do it. Even deep learning model. Right? If I go back to the deep learning model here that's finished, there's a button that says Java model. Also to pay for display. And here's your neural net. Here. Activation. Oh, sorry. Here we go. This is the predict function. And it fills up some initial value to 0, and then normalizes the data, computes some categorical offsets. That includes activation functions, like weight, or activating spectral multiplication as the bias terms. That's this is the activation function. In this case, it's a rectifier. It does softmax, and then that's it, then it makes a lane. Okay. All this code is self-contained in a little jar, and in this plain Java file. So it's very handy. That's one of the reasons to license H2O, that you get this feature, that you get support and so on. So if you're an enterprise interested in H2O, please talk to us later.
So this feature is not included in the free version?
It is. But we encourage you to talk to us either way, because there's very deep reasons why you would want to license this. And one of it is that you get to have direct feedback into the roadmap, and you get to have your problem solved first. You get to get your new model features implemented. If you say, oh, I need this and this, I need this in Hadoop, in Storm, or whatever, I don't know what to do, it's more likely that we answer your questions immediately if you're a paid customer. But you can do it on your own. You just download it, use it for free. It's Apache 2. Lola, you can take it and make your own company today. It's all open source. Yes?
So, am I correct? I thought you said that each of the machines is training a different deep model.
They all start with the same one, and then in one map phase they train it, and then it becomes slightly different, and then they average, and then it's again the same. And then they get the same one to do the next map. It's always like this. They always get together again. So this is a parallel scalability from 1 to 63 nodes. One node was dead. There was some system they got to try it on. But basically, it scales reasonably well. There is, of course, some network overhead because you have to communicate. Comparing it to one node is not quite fair because one node has 0 communication. So from 1 to 32, it's like an 18 times speed up. But next time I'll plot it from 2 to 64 because they all have some communication. There will probably be a fair comparison than to compare against the one that has no communication. This can also be used for other problems like text classification. eBay has like text that people type in when they sell something and they want to know is it actually a Rolex or what is it? Is it a ring? The people that sell something, they say this is a ring or a Rolex, and eBay wants to check if that's actually true. Otherwise, they post the thing in the wrong category. It will never get sold. eBay doesn't make money when they don't sell it, and so on. So now they have a bag of word vector that says which word is used or not, And if this vector, that's like 8,000 columns, right? There's a lot of different words you can use. With that, you have to predict, is this one of the 400 classes that you can be? Is it like a Rolex or a diamond ring or whatever? This is just the jewelry section that has 467 classes. And then the test set was a little smaller and only 140 classes, but still you have to predict which class is it every single time out of the 460 possible classes that you trained on. And after running this for, I think, 2 or 3 hours here on 4 nodes, only for 10 epochs, like almost default argument. But if there's a couple options, you can see them in the slides later. Basically all default except for 3 layers of 1,000 and a little bit of L1 penalty. The rest is all automatic. I did some dropout, but not even sure that was important, but who knows. And it ran fairly well. It actually got to an 11% error on the validation data. So 90% of the predictions got the right class out of 140 or 143. So it's pretty good to get the right class. This, of course, can be tuned more and so on, but I'm just telling you that this is very efficient for many classes because in random forest you have to build 140 models that each say, is it this class or not, is it this class or not, is it this class or not. There will be a lot more work for a regular decision tree or gradient boosting method. And GLM in our current implementation does not have multi-node. So this is one of the few methods that we have at least that does well for many classes. And another benefit, by the way, is that you don't need to train the whole data at once. You can train 1% of the data. That's already a good model, right? You can just stream through it. You can just keep going fractions of the data at a time. You say, I want to train for only 30 seconds. Let's see what I get. And no other method will give you that easily. Yes?
Yeah, probably related to what you just said. What's the minimum set of rows that you need to have to train a reasonable model, right?
Depends on the data complexity, right? The intrinsic structure of the data. It's very hard to say. For Iris or something, you need all 120 or whatever rows. But if you have like Higgs, if you only use 1 million rows instead of 10 million, you will not get to the 80 whatever it is. You might get a little less. You get maybe 2 or 3% penalty. So you can see that more data helps. Especially deep learning benefits from more data because you can imagine it pushes a little harder into those corners that it needs to learn. Right? You really want to send as many examples as you can for these supervised problems. So this is where big data will help. And streaming is a good thing for big data. We can checkpoint it about more next week, and if new data from next week, we can keep training an existing model, and it keeps getting smarter every time you add new data. It's like a moving window if you want. You can always have an up-to-date model. So let's do this example here live in my R session, just to show you that R. So I go to R Studio. I'm sure it's a little small for you guys. Sorry, but you don't have to read all this. It's basically doing, can you see this at least? A little bit, right? So it says library H2O. It says connect to the cluster. In this case, it's my one-node cluster on my laptop. I'm loading the data set, which is MNIST digits. We're seeing what are the predictors, what's the response. In this case, we just remove the response because we do unsupervised training. We don't need the response. We don't need to know which digit it is. We just need to know that it's data. So we actually remove the response there. Minus rest means response goes away. Now we train an autoencoder here. This is an autoencoder. An autoencoder means compress the data into a network with few neurons in the middle, less neurons, or fewer neurons than there's input to of the data, and try to get back to the full dimensionality of the input. So you're trying to learn the identity function, but you're forced through a narrow neural net, which means it's like a PCA, principal component analysis. It's just non-linear. Try to come up with good features that somehow are able to represent the structure of the data without seeing everything. Just imagine this neural net in the middle, it has a few neurons. In this case, it's 50. Those 50 neurons, those numbers, uniquely define what happens after that, right? They make up the output from those 50 numbers. So with only 50 numbers, I'm making up 784 numbers. And if this is a well-trained model and the data has about dimensionality of 50, which in this case you can see with PCA, then there should be a reasonable chance of being able to reproduce the data, but only roughly. You only see kind of the rough idea of the data. You don't see every small scratch on the paper. So with this fast model, we only did one pass over the data. We now know what's a typical digit from the training data. And now we're going to make a reconstruction of the test data, and we're going to see if you pass it through the network, what comes out. Does it look like the input? Like, is the test data also matching that model of the data? Or is the test data different? And obviously it will roughly match because it's the same distribution. But those digits that are kind of the worst in this reconstruction, they don't fit the training model. They're different digits than what's in the training set. What does it mean? It means that they're ugly digits, right? Because you have 60,000 digits. If you find something in those 10,000 that's totally different than those 60,000, it means it's kind of an ugly writing. So we want to identify those. So we compute the reconstruction error, and then we actually compute the numbers that come out at the end, the 784 numbers, the reconstruction itself. And now we make some functions to plot this stuff, plot digits. And now we can plot them. We plot the good digits. These are the reconstructions that come out of the end of the neural net. These are the good digits. You can see they're all ones. They're easy to reconstruct because these are the easy ones. Makes sense. Let me go back to plotting the rest here. All right, here we go. This is how it looks. The original data, right? The original data and the reconstruction is similar. So this is the reconstruction. That's the real data. Obviously, it matches very well. Then now we go to the next level. These are. That was actually, by the way, this was the top 25 or so best reconstruction. These are the middle 25 out of 10,000. These are like roughly okay, but not quite great anymore. So they don't look that easy to recognize. You already see some of them are pretty ugly, right? This is an ugly 2, but mostly the 2 and 1 and 8 and 3 and so on, they're reasonable. It's still recognized. Now we go to the worst 25 reconstructions. You almost have no idea what they are. And in reality, they also are really ugly. This is an ugly 2, an ugly 8, and so on. This is very ugly. What is this? Right? So this is like every time you run this, you get a different answer because of multi-threading and all that. So this is life. This is what it is. But I've never seen it not work. Right? It just simply finds ugly digits, and it doesn't know anything about digits. There's no image recognition technology built in, no convolutional layers, anything. It's purely based on the numbers of those digits. And of course, if you have a fraud data set or something, this might work as well. All right, so this was from R. This is just R code, right? As you can see, again, this is just R code. All right, let's get back to the Higgs problem. So what do you think deep learning can do? Instead of 73 or 76 as we saw, you already saw that it could do 81 earlier, right? This model that we trained. So let's see how much we can do. Let's go back to the cluster. And let's look at the models. So the last one finished. It got to a 83.6. That's pretty good. Now let's compare all the different models. There's a multi-model scoring tab there, where you can say models. We have all these models here. And now I select them all, and I say score on the last holdout set. That's what we call the final test set, right? The last 500,000 points. Now it's scoring them all and computing the metrics. Then it displays them here. It's a little small in this screen, but you can see that this is not as great as Random Forest. This is GLM, that's the worst. I'm not a GLM, this was the one I ran earlier, this is the one I just ran with you earlier. This is GBM, also not that great. This is deep learning with 3 layers of 500. That I ran earlier as well, that's 84. This one I just ran the 200, 200, 200, and I did 50 epochs. That's after the checkpoint restart. And that also got a 53.6. It's almost as good as this guy here with 3 layers of 500. This had 100 epochs. So yeah, it's kind of a balance, right? You have more layers, but smaller neurons, or you have more neurons but fewer layers, or maybe you need both. Ideally, it's like 6 layers with 500 or so. And when you do that, you get numbers even higher than 84. And if you wonder, like, what's the benefit here of all these methods, you can actually display them here. You can plot, let's say, the training time versus the AMC. You see all these different models here. See, this was the deep learning model, the one with the 500 layers that took a full hour to train. It got the highest accuracy. But here you see that this orange one is also deep learning. But it's faster than these other ones here, but it's actually higher accuracy. These other ones are the random forest, and GBM, and down here is GLM. So you get like an idea of training time versus accuracy. And this is a useful display. So I showed you this here, and this. Basically, the conclusion is that in even a minute or two that we saw earlier, we beat all the other methods, right? And if you run it for overnight, then you actually get 87. I got to 87. I didn't get to 88, so the paper got to 88, but they also had half a year of time to tune all these knobs and stuff. And I just did this on a weekend once. But it basically shows you that deep learning is very powerful. You can get a significant lift over these other models here, 7 to 6. So 10 points in the AOC chart, that's significant. So if you're interested in running stuff yourself, there's Kaggle scripts. Who has ever done a Kaggle competition here? Nobody yet? 1 or 2? So Kaggle is a data science competition. They have a bunch of challenges out at any given time. So right now you can say, okay, I want to do one. And you can try to start your own data science riddles, basically. They're telling you, here, do this, right? If you don't know how, you have to learn everything. If you do know how, then even better. You can see how well you're doing against others. If you don't know, then you can read the blogs and so on. So all of these are links to actual posts that I posted, actual code, our code, run H2O for these problems. And this is the one we just finished, ranked 26 out of 1,600. And there's a one that we just started, and they're currently first. I think you might be second by now, but then I'll take a screenshot of the first. It's after only a few weeks out of 3 months total. But you can see it's fun to like do these things from time to time. But currently we're busy with H2Dev, which is the next thing. But before we go to the next thing, let's go back, relive H2O World. For those that haven't attended H2O World, there's a lot of videos by people like Trevor Hasty, John Chambers, Josh Bloch, all these people, and there's a lot of customers talking about how they use H2O. There's a whole day of us teaching all this, right? Supervised method, unsupervised, advanced topics, use cases, marketing. There's enough material out there to keep you busy if you want to watch the videos or look at the scripts to learn or H2O guy. There's a lot of stuff. There's also a Kaggle competition panel that we had with some of the world's best Kagglers, like the X#1 was actually there, talked about the secrets and so on. So those are people that know what they're doing, and that alone is worth watching that video. There's a bunch of kit books. I'm not sure we have some in the back somewhere, but we have like a deep learning booklet. If you want to know how to use deep learning properly, you can just click here or actually take the book with you later. And same for R, all the tricks, how to use R, and H2O, of course, the R aspects, tricks and tricks. And this is the actual H2O World training day. We had a bunch of scripts and examples. So this is the next thing. It's called H2O Dev, or sparkling water. H2O-Def is our internal name for it. That's basically a developer-friendly version of H2O. It's a rewrite designed to make everything cleaner, to get rid of technical debt, as they call it. Just like you learn from the first iteration and you rewrite it to have a clean slate. And H2O-Def will now also have Python as an API, not just R, JavaScript, so you can write your applications from a web server, or you can have a connection to Spark, RDBs, and directly in the same JVM connect to the data that comes from Spark, and suck that into H2O. And this is just a screenshot. It looks a little small here, but I'm going to show you that in a live demo. So what I need to do first is I need to go to IDEA here, or developer environment, and I need to kill the H2O1 instance, and then start H2O-Def, a new one. On my laptop, okay, it's just a small example. Now I go to the local host, port 54321. I see this. You say, what is this? Well, this is H2O Flow. Who knows what IPython notebooks are? Those are like one thing at a time. You type in, something happens, next thing, and so on. This is similar, except that this also has both way directions, so to speak. So whatever it shows you, the code that it generates, you can then edit and regenerate something new from it. It interprets your code, and you interpret its code, so to speak. It also has mouse usability, so it's not just text that comes out, it's actual charts and things that you can click on, actual user interfaces that are being generated by code. So this is very simple to use. I can say assist me, I don't know what it is, it's me. Here. I can say import files. I can type in small data, and I can say prostate. Okay, and I can say, well, let's say this one here, prostate csv.zip, import. Okay, parse it. It says, all right, this is how it looks like. ID, capsule, age, race, and so on. That's my prostate data set. Parse it. Now it has a job. I can look at the job. It says it's done. Destination key is prostate. I can look at it. Here you see the data. Each column has some kind of number of missing, number of zeros, number of infinities or whatever, or min, max, mean, sigma, type is either integer or real. There's no cardinality because there's no factor levels. If you look at the summary, you can say, let's see the summary of this guy, all kinds of stuff, right? But what you can also do with this, you can build a model on it. You can build, let's say, a deep learning model where we want to predict capsule, and we ignore the ID because ID is just whatever. It should not be predicted the number of the patient, right? So classification, yes, we're going to predict the capsule, and let's just say go. All this other stuff you don't need. It's all explained, by the way. And if you do something wrong, it will explain. Now it should be fine, it should be running. Now that this is running, let's see what it's doing here. So it's building these learning here in the background. What is in my laptop is small. It computes a lot of stuff. I think it's mostly computing metrics right now. But you see a scoring history and status neuron layers and all that. But that's just text mode. Let's see whether we can see this in the graphical. So here is the model. I click on it. I can say expect. And then I can see here status of neuron layers. Here we go. You can see the same thing that we saw earlier in HQ1. How many layers, average weights, and so on. Then I can click on the scoring history. And I see the training duration, 26 seconds to train a medium rows. That's the training mean square error per down, the training R square, AUC, classification error. In the end, it's zero. It's perfectly trained from everything. It just memorized the whole data set basically because it's small data set. It's just repeated over and over. So let's look at the trading metrics. Here it says that's the average error, the AOC, and GDM of 1. And now I can plot it. I can plot the scoring history. I can say plot me as points. The x-axis is like the duration, let's say, and that y-axis should be AOC. And I get a chart that's, oh, it's already up there. It's like a 0.999. So we're still working on this. This is like all preview, right? But you can see that this is powerful. You have code that's generated, and whatever comes out here, you can then modify if you want to learn how to program in this language, or you can use your mouse. I never typed anything, as you can see. This was all with the mouse. And you can script stuff. You can write the same thing in Python or R or JavaScript. So this is flow. Python looks like this. It's a little small as well, but basically it's regular Python, right? It's import something, and then it's commands just like Python notebook style stuff you do for Theano or for scikit-learn or standard Python. Of course, this is still just REST calls to the server. All it does is it builds a string and sends it to the server. But your string can have expressions. It can say, change your data column to the sign of these other things, like this plus this square minus that. That whole expression gets shipped over the wire as a string. H2O takes it into a map that's used over the big data on your billion rows and computes that expression row by row and puts it into an output vector that then you get a handle back to here. You only get a key back saying this is the object in the store that now contains the number. So no work will actually get done in Python. It's just the way you talk. It's just your language. All right, so we're almost done here. You can participate, of course. If any of you wants to join this effort, you're welcome to play with it. It's all open source. If you say, I want to have better k-means, or I want to do convolutional layers to show that deep learning with MLIS can be better than quantade, which it can be, that would be a good thing. Ensembles, but just use us for Kaggle, for example, or for your job, right? Maybe you have data science responsibilities, or just want to predict what's the weather like tomorrow, or what fantasy football team is going to win. You can do that, right? This is all fairly easy nowadays. So yeah, go to GitHub, check us out. We have two repositories. One is H2O, one is H2O Dev. So from now on, everything will be H2O Dev. But we're in the middle of this transition. So today, I would suggest you still use H2O1 to go through the examples. Once you get an idea of what's possible, try to do the same thing in H2O Dev. But from a month from now or so, everything will be H2O Dev. So try to migrate over to the new version. But it should be fairly seamless because the same ideas still hold. Parameters are the same. Deep learning has all the same parameters. It's all the same. It's just a slightly different way to call it. But that should be it. Thank you so much. So if anybody wants to see something or has a question, that's not a good time for it.
I have a question. So for the general linear model, do you have the module as well?
The generalized linear model, Hojo, no. Right now you get the coefficient vector, and you just have to do it yourself. But it's not that hard, right? For a logistic regression, it's just an exponential function, 1 over whatever, the sum of these things. And you get those numbers back in R with the coef method. The coef of model, you get a vector of numbers. That's very easy to just write one expression and compute. But we can help you if you want, but we don't have Java code right now for this simple model. But if you have the numbers, you basically have the code. I'm guessing the first.
So, if again on the regularization of the deep models, if all the nodes are going through the same data, how come you get that speed up?
The question was, how do you get to speed up if all the nodes go with the same data? It's a good question. There's 2 or 3 ways to run this, by the way. You can have the data distributed. Every node has different data. if let's say you have a terabyte of data, you have 10 machines with each 100 gigs of RAM, right? And it's all numbers, they cannot be compressed, because it's all doubles the full precision. So you have really 100 gigabytes of data on each machine, you need to process it. You can have the 10 different models being trained on different data by definition, and then you want to average that. If it's small data like MNIST or Higgs or something, a few gigabytes, you can send that data to everybody. That's the default option. The default is to send the data to everybody. Then all these 10 or whatever, 20, 50, 100 models that are being built in parallel, they all are pretty smart because they all learn on everything. The only difference is the initialization. No, sorry, it's not initialization is the same because they share the same one. The only thing that's different is the race conditions in that case. However, if you say I want to pass over 100,000 points per step out of my 100 gigabytes, then maybe that's only 1% of the data. So you're sampling up for each pass. And each machine has a different seed for sampling. So they will see different points, and they have, even though they have the same full data, they only see a different subset. So they're also training slightly different models. So there's always a benefit of adding them. In the worst case, you pass over every single point that are all the same points, then the only difference you'll get is that these 32 threads compete the race conditions differently than these. So your model that is slightly different, but not too much. In that case, your speed up is just because you process more points overall, but it's certainly not as good as if you had some smart thing that somehow cut up the work into 10 different pieces. Right? So this is just one way to parallelize. We've seen fairly good speed up. So like the Higgs problem, it will take a lot longer to do than one node. But it's actually fairly effective, especially if you do this subsampling on each machine. And that's what is the default option. Yes?
So just a very simple question for the MNIST digits. I mean, what's the data itself there that is used and reproduced? Is it like, what was
It's
the...
28 square pixels. That means it's 784 columns, and each has a number from 0 to 255. It's a grayscale.
It's a grayscale. Okay.
So it's maybe 10-20% fill rate, right? Mostly zeros, but those that are non-zeros are like gray and then mostly black. And you have to decide from those numbers that this is a letter 6 or 7. And somehow the neural net learns all that, right? Yes?
How does this implementation compare with the GPU-based implementation?
You tell me. I didn't run it.
Was there any comparison done?
Well, what we see is that nobody comes to us and says your deep learning is not great. I did not do a benchmark study myself using GPUs. I know that GPUs are fast. So if you have like MNIST and all you do is MNIST and you want to solve it fast, you take one super good GPU and just, that's it. But if you have a data set that's on Hadoop, on your 20-node cluster, and every day it gets updated in Hadoop, and you don't have a GPU there, then this is a better solution. So it really depends on what you want. So this is not just because this is all of H2O that you're getting. And there's more things than just deep learning in it. But deep learning with all the threads and all the machines is a lot of compute power, especially with modern GPUs, CPUs, it's fairly fast. Of course, modern GPUs are also great. So if you had a Hadoop cluster full of GPUs, then you'll be even better off. And then H2O is not the solution for you right now. But you saw earlier, it's a ticket in the Jira system. So I'm actually planning on doing that sooner than later. But that will be OpenCL through a Genie call, which means you still have to pass the data over to the C code that basically that runs, right? And back to Java, so you cross the JVM barrier. So you have to basically bundle up the weights, the model, and some data, and say here's 5 gigabytes, now train, and come back to me in like 20 seconds. Then you're done with some training. And so on. So you have to think about where the data goes when, and that's more work. And it depends on the data, right? Maybe you give me a super big data set where these few gigabytes on the GPU are never enough to actually see anything. Then it's a lot of transfer back and forth. But it might still be worth it if you have a fast enough GPU. So it's a balance between ease of use and ease of implementation versus I would love to see a comparison how this holds up against the GPU solution. beauty of this is you can run this on big data sets in Hadoop and just compare it against random forest, GVM, or logistic regression, for example. And all of that runs in the same infrastructure, on the same data set, and everything is distributed. So you benefit from, if you have a 100 node cluster with modern Xeons, then you're going to be fast. Yes?
This is a question that relates to the previous one. Do you use any algorithm framework?
No. I can show you. Basically, it's all our own code. So this is the matrix vector multiplication code. Can you see this, or is it too small? You get an idea. So this is a loop. There's two loops for matrix vector multiplication. We have two for loops. What we do is we do some partial sums in here. So instead of saying add and then add and again add each one of these terms to this one sum, keep adding one thing at a time, we add 8 partial sums. So you can add them out of order. And at the end, we add those 8 numbers together. So there's tricks like that that make it faster. This alone is like a 2x speed up of the bandwidth. Of course, a GPU library or so could also do similar stuff. But this is as fast as it gets. This is Fortran speed, C++ is all the same. This is as fast as it gets on a modern CPU. But it's still memory limited. So if you have a big network and it's all in main memory, not in level 1 or level 2 cache or level 3, if it's all in main memory, then it's going to be slow. Then you have to do random reads and writes to the main memory. And that's where the GPU is faster. Because GPU has a few hundred gigabytes of bandwidth nowadays. A modern CPU, I just bought one by the way, at like 60 gigabytes. Not bad, right? At least the modern DDR4 solutions have quad channel. And Cliff is one of those workstations here too. I mean, they're not too bad, but it's still a factor 4 or so off. And then the number of compute units is also vastly different. And GPU has 2,000 cores, CPU has like 8 cores, 16 cores. So definitely a GPU is faster for this kind of work. But we at least use all the cores and use all the cores on all the machines. And we also have a couple of ifs in here, as you can see. It says if this expression is true, then it would otherwise don't. And there's some things in there like the back propagation as well also. This is forward propagation. In the back propagation, if the gradient is 0, because you rectify it as negative, you don't do anything. And that if is important for the CPU because it's not worth doing the extra work multiplying zeros. On a GPU, you don't check that if, you just do it anyway because you're fast enough. But you're saving about a factor 2 here by only doing those that are non-zero. So there's a couple of optimizations we already did to make it fast. But I would love to see comparisons in the field. Also, if you have a GPU solution, you might not have the adaptive learning rate, the automatic standardization, and so on. So some of those GPU solutions are more hacker-oriented. If you're like an expert coder, you can use them. And I believe this is an easier solution if you just want to click on it and it runs. So there's a pro and con for each of these approaches. Yes?
What other languages do you generate the code with?
Oh, we only generate Java code right now, but it would be easy to produce C++ code or
For Objective-C, for iOS, how do you?
sorry?
For iPhone.
For iPhone. Yeah, I mean, it's not that hard, right? The generating code is also in the open source project right now.
Code generator?
The code generator, yeah. It's just some wrapper. I mean, in my case, it's neural net weights and stuff. You just have like a for loop that you can write to multiply, right? You can write that code in any language. Any more questions? No? Right. Oh, one more?
Yeah, so how far is the H2O in terms of the Python implementation? How good is the Python support currently compared to the H2O?
So we had a meetup yesterday by Cliff, our CTO, and he wrote big parts of that Python interpreter. and he's a compiler expert, right? So I trust that it's good. We haven't released it officially. I think today was a press release announcing that we will release it for Strata next week. So it's fairly close. You can definitely try it today. We have unit tests running all the time, right, in the background. Like, this is running code. But if you have like a feature missing, maybe, I don't know, you want to compute the hyperbolic tension or something on the distributed data, maybe we forgot to implement that, right? So there's a couple of things like that, but nothing is a deal breaker, so to speak. It should all be fine.
And how far along is Flow in terms of your development map, roadmap?
I would say it's also over 90% there. Like, there's only the last few things to connect the output of the models, right? What you saw earlier, the model output, you have to do this for all the different models and show all the confusion matrices and errors and stuff. And we're currently wrapping it up, so it should be ready anytime. So yeah, this was a major work for us to rewrite everything, right, in this clean new way. And many things have not changed, many things have changed. And we have to maintain two code bases, but the goal is to get rid of one as soon as we can and freeze it in place, which is it's a pretty stable workhorse. It should remain that way. Now the new version can now like reach parity and then keep going up and have new methods, new algorithms, new features that was not possible before. For example, versioning, multi-user, LDAP, all kind of stuff, database connectors. There's a lot. Some of these are enterprise offers, right? Where paying customers get a couple extra features. But this is all being developed right now, so you don't hide anything from the current database, current GitHub repository. But in the future, there might be multi-user support or something like that, or model comparison, extra features on top of the free version. But it's not clear what that's going to be yet, at least not to me. All right, great. Thank you so much for coming.